31. First, they tell us that the mean height was 64.3. So mu is 64.3. We're going to get into a lot more here in the next couple of sections. A lot more new symbols. So you got to remember the old ones. Or you should know the old ones already. 2.6 is our standard deviation. So normal height, 64.3. Any of the females know how tall they are? 5'4". So 5 foot 4 inches. 5 times 12 is 60. Plus 4 is 64. Are you pretty close to the average height?
Yeah.
So we have this. Don't forget, we didn't need to do this on this one, but because I know what we're going to have to do today, and some of it's looking at these graphs. If we were going to draw this graph, what number goes right, or if we were going to draw the normal curve, what number goes right in the middle? How many spaces do we go out on each side? 3. Go out 3 standard deviations on each side. To go out a standard deviation, you just add that 2.6. So the first one over here would be 66.9. Add another 2.6 to that, that'd be 69.5. Add another 2.6 to that, that'd be 72.1. And if we went out the other way, I'm not going to subtract them going the other way, but our normal curve should look something about like that. Mean right in the middle. What's the chances of us picking a female in our classroom and their height being right there? Unlikely. If you're out more than 2 standard deviations from the mean, that's unlikely. What's the chances of picking a female out there? Very unlikely. All right, so remember all that. Some of the stuff we do today is going to deal with some of that. This one just said, for part A, what height represents the 95th percentile? So we want the 95th, is that what it said? Yeah. We want P95, so that means we want 95% of the data to be to the left. So we're going to be somewhere where over this way is 95% of the data. Or the area under the curve that way is 0.95. You'll have to help me out because I don't remember with the calculator. What do we put in on the calculator? We put in what, and what? If we're going backwards. Wouldn't it inverse norm or something? Is that right? Not been that long ago, has it? Nobody remembers what we put in? We could find the z-score, but I think we could also just put it in the calculator the way it is.
So it would be inverse norm area minus the area.
Just put it in the area?
Yep.
That's all we got to put in?
So that has
Find x. So let's try that and see what we come up with. So grab your calculator. You got to hit second. The bars, right? Second bars, go down to inverse norm. Put in, what's our area this time? 0.95.
I need the mean and
You do?
No. That's the x value.
Now, Jacob's sort of right here because 1.64, think about what our answer is here. 1.64, so are we gonna have a woman that's 1.64 inches tall? Probably not. This is a what? That's your Z-score. This time we don't want the Z-score, we want the actual height, so we're finding the X value. So what else do we need to put in there? You still put area first? Still put area first, is that right? So you put in area, then you put in the mean, then you put in the standard deviation. So this time, what are we gonna put in our calculator? Remember, this one, doing this way is if we're looking for the Z-score. Doing it this way is if we're looking for just the raw score, the score with the X value. Area was 0.95, what's the mu? 64.3, what's the standard deviation? 2.6.
68.57.
So we're saying 68.57, we'll say 68.6, close enough. 68.6. 68.6 is going to be somewhere about right in there, right?
Yeah.
Does it look like 95% of all the women are going to fall in that area right there? Does that make any sense? Give me a number that wouldn't have made sense if we got it as our answer here. 62. That been down here somewhere, like in here. Well, 95% of the women aren't going to fall below height of 62. Part B, what Part B say? What height represents the first quartile? The first quartile. So the first quartile, what is the first quartile again? When you find quartiles, what are you splitting it up into? Splitting it up into quarters, right? So you got 1 quartile, 2 quartile, 3 quartile, something like that. I don't know if those aren't probably right. The third quartile is actually going to be here since we just found that one at 60 or at 95%. So if we got this, what's this first quartile? What percentage of the data falls below the first quartile? 25%. So 0.25 falls in that range there. So it'd be the 25th percentile is the same as the first quartile. What are we going to put into our calculator this time? What's your area? 0.25. What's your mean? 64.3. What's your standard deviation? 2.6. Somebody punch all that in, what you come up with.
With 62.54. Inverse norm, whatever, and then that.
Yeah, this and that. So if we're going backwards, if we're actually trying to find either the Z-score or the actual X score, the raw score, then we're doing the inverse. That's what that, so instead of doing just the normal CDF or normal PDF and just doing the curve, we're trying to go backwards. So we're saying, all right, we have the curve, we want to go back to the numbers, find the numbers. Malachi, what'd you say it was?
64.8.
62.54.
54, so 62.5. If I subtracted off 2.6 to go down this way like I should have, let's see, that's 61.7. 61.7. So they're saying 25% of the data will be in that range right there. Does that make sense if that's about 25% of the data? Yeah, probably. My graph was drawn a little better maybe. Now be careful, because when you're looking at that normal curve, can you just split it up into like fours? Going across down here at the bottom and trying to make these even? There's going to be more area in here than there would be in here, right? So when you're splitting it up into fours, that middle area is going to be a little narrower than the outside areas. Other questions? So you're asking now if all of you forgot all this. We've got a test coming up here pretty soon. Matter of fact, what is section 5.4 is today, then 5.5. I believe 5.5 is the last section. Yep. 8. Problem 8. Use the standard normal table to find the z-score that corresponds to the given cumulative area or percentile. If the area is not in the table, use the entry closest to the area. If the area is halfway between the entries, so on, so on, so on, so on. So it's saying use the standard table. Do we have to use the table? Do we want to use the calculator instead? So let's use the calculator. So problem 8 says 0.0046. So we want to find that. What did they say find? They said find the z-score, right? So this time we're going to put in inverse norm, and we're just going to put in the area. So we're going to punch in inverse norm, then punch in 0.0046. And that should tell us our z-score. So what's the z-score this time? Say again? -2.6. Now, let's make sure that this makes sense. -2.6. I don't know. That doesn't seem right. So if we got this, we want the z-score that has an area. If we look at this, this is less than 1%, right? So we want less than 1% to the left of the z-score. So we're going to be way over here because we want this area to be less than 1%. Does it make sense for it to be a -2.6 way over there somewhere? Yeah, that makes sense. -2.6, -3 would be like right here, right? And what do we know about scores that are out past -3? Very unlikely. Other questions? 20. Problem 20, find the indicated z-scores shown in the graph. Convenient use technology. So again, problem 20. Same idea on this one, except we're on the other side. So they give us this graph. My normal curve this time doesn't look very good. And this is 0.0233. And we're looking for this z-score. So same idea, let's do this. Inverse norm. What are we going to put in for our area this time? 0.0233. Malachi is going to watch closely. Quit talking to Mikey back here so he can see this, because I'm getting ready to show him how he's going to mess up on this test coming up. Negative, what is it? -1.98. This is why I want Malachi to watch closely. -1.98. That z-score is going to be right in there. We were looking for this z-score over here. So can that be the right answer? What did we do wrong? What's the calculator tell you again? No, I mean, what's it tell you as far as when you're dealing with these areas and stuff? Only tells you the area to the what?
Right.
To the left. So we need to switch this around, and we could just switch it, switch the sign here, and it should be positive 1.98. But to be on the safe side, probably when we started off here, we actually didn't want this area. We wanted to tell the calculator this area over this direction so that we know that it's giving us the correct number. So what would we have to do to this area to see how much area is over here? How much is the total area? 1, right? So what do we do with that to find this area over here? So do 1 minus that. Somebody do that real quick. 9767. Now, we can take that and we're going to hit inverse norm, punch that into the calculator. 1.989. So it does gives us the positive answer. But now, does that make more sense for that z-score right there to be 1.98? Does that look like about a positive 1.98? Yeah. Remember, you're starting off for z-scores. You got 0 right here in the middle. Then you go to 1. Then you go to 2. Then you go to 3. -1, -2, -3 on your normal curve every time. Next question. Oh, I'm sorry here. I forgot all about it. Other questions? $16? 16. Somebody read that to me. What's that say? 80th percentile. All right. So when we're looking at the area, we're looking at the area on our normal curve. What's that telling us? Where are we going to be at? 80th. Where's that at? Somewhere about there. We want what? What's that telling you? That you want 80% of the data to be on this side of your z-score, or where you're at. So we're trying to find that z-score right there. Somebody give me an estimate of what you think that z-score might be before we start. 1.7? 1.8, somewhere around there. All right. We know it shouldn't be like a negative 2.1 or anything, right? Because we're 80% over this way, so it should be over in those positives somewhere. All we're going to do on this, again, since we're just finding the z-score, inverse norm, and all we got to put in is the area. What's the area this time? 80. So I put in 80. 0.80. If you put in 80, it's going to tell you some stupid answer. 0.841. So that's our z-score. Are you guys very close? No, not really. So you need to remember your empirical rule when we're doing these curves. You got your mean right here. How much is in each of the first standard deviations on each side? We might have to have a quiz on the empirical rule here pretty soon. Anybody remember about how much is in each one of the next ones? 15. 13. If you can remember that much, and that's going to help you. If we wanted 80% this way, that's 60, 68 plus 13, about 81. So it's going to be somewhere just short of that. Other questions?
Was there anything else on the homework that we missed? Or was that all we were doing?
That's all we were doing on that part, on that homework.
No, like, the,
Homework, the other page?
Like each thing, like did we go?
That, yeah, we went over basically all of it. Alright, this is what you're going to do. You have those numbers that you got from the back of the book. They should be 5-digit numbers. What I want you to do, I've done mine up here already. You're going to come up here and you're going to grab this pen, you're going to write yours in. But first, before you do that, before you write yours in, you're going to take your 5 numbers, and we're not using it as a 5-digit number. We're using it as 5 separate 1-digit numbers. Alright? And you are going to add all of them up and find the mean. So find the average of all of them. So you're going to add them up, find the average. X bar stands for what again? Mean. So you're going to write down your 5 numbers with a comma, just like I did here. And then you're going to come over here and you're going to write your mean. Then you're going to write down your second group of 5 numbers. Then write down the mean. And we're going to make a big long list of these. So go ahead, find your mean, then you can come up here, write in your 5 numbers with the commas, and then write in your mean for each one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's 13 of you, plus me is 14, so there should be 28 sets of numbers up there when we're done. I promise you, because the stuff that we're going to do today confuses me a little bit. It confuses me a little bit. What's that probably tell poor Camden here?
It confuses everybody.
So you might want to pay real close attention when we go over this stuff today.
Wait, I'm like super confused. So we take the 5-digit number, is that what we're doing? And putting commas in between each of the numbers?
You listen.
And then you find the
You
mean
were
of each.
asking me a question.
oh, right, so it's just like the other. That's not right.
Hey, so we add them up and divide. Divide by 6. Divide by 6.
Why divide by 6? My dog's dead.
6 numbers.
Yeah, it magically takes 2 numbers that come out to the same thing. Yeah.
43. Oh, yeah, I did do it.
If you run out of space, just move my desk over and start writing in that second column over there. Lucas, do me a favor and write with the other pen.
I can't see.
Because you can't see that. I'm trying to record it for posterity.
You can Indian company. You can Asian company. You said Indian company.
So, hey, restroom real quick.
Oh, there's C in it.
It's a freak. It's a freak of you.
Malachi, Julie put what? You're supposed to put snow.
It's fried.
Hey, don't let him go, Mikey. Don't let them go.
Nice comment. Why'd you guys start writing so big? We were doing well, and now we're gonna run out of space. Mikey's gotta have an extra line for his commas.
You forgot them.
Oh, I think it's real short. You got caught. Oh my goodness.
Yep.
There's a lot.
Do we have to write it on that, or can we write it on the board? Or
Write it like above.
You already
You wanna write above it?
like up there?
Yeah.
Alright. Oh wow. I hate using these. I've used them forever.
Sometimes I can't read his writing, so I gotta write it big.
Oh shoot, I forgot a comma.
Who did the 506 word? You did. That was you. No, I did 51363. There's like there's tally marks under it. That's not a comma, those are tally marks.
I forgot one.
So if you like, write your first one there, then go over to the other column, and then Dalton can write his two
Numero.
in the other column also.
Oh, wait, we have to have 2 cents a number? Yeah, that's what I messed up with. Okay, bro. Right at the top. How to look at it.
Mikey, he's as smart as you are.
No, you can't put a comma on the number. It's fine. There's an L. Okay.
I got it, 6.6 right there. It's hard to write right underneath that, the sensor there.
Thanks.
Alright, here's where you gotta listen. Because the stuff that we're gonna cover today, I'm telling you, it's not easy to understand. But if you understand what we're getting ready to do right here, you'll probably be alright all the way through the section. Okay? What we're doing here is we're randomly picking 5 numbers out of what set of numbers? What was our population set that we had here? All the possible numbers that you could have had up here. 0 through 9. So we're picking from that set right there, 0 through 9, those numbers. Somebody help me out real quick on your calculator. Average up 0 through 9. So go 0 plus 1 plus 2 plus 3 all the way up to 9. And let's find the mean of that population. 4.5. Anybody else get that?
Yep.
So the mean of our population, the sets of numbers that we could have picked from, 0 through 9, the mean is 4.5. What we're doing, because, and we've learned this throughout the year, can we usually get the whole population?
No.
No.
Example.
So what we've done is we've taken samples of that population. Now the stuff that we're going to cover today is going to show you show you that you really don't need the whole population. You could just take a whole bunch of different samples. And that's what we're going to try to prove here. We're going to cover this central limit theorem. And that central limit theorem says if we take enough of these, which we don't have quite enough, because you got to have at least 30, and that's going to be one of the things that we're going to talk about today. But if you take enough of these samples, guess what the average of all these means that you guys wrote up here should be? It should be exactly the same as that. And all these means up here should form a normal curve, getting closer and closer to that mean of 4.5. Now, if we were to do this, the 0 through 9, if we were to do like the probability distribution of 0 through 9, it's not going to give us a normal curve. It's going to give us a curve that looks like that, because what's the chance of picking 0? Same as picking 1, same as picking 2, same as picking 3, so on, so on, so on. So even though our original data wasn't normally curved, we didn't pick 5 every time, or most of the time, even though it's not normally curved, these sample means, the means of all the samples that you guys picked, should be normally curved around that mean of the original population. So let's see this real quick. I was going to bring my calculator out and I forgot. I'm going to add up all those means. Somebody else do it too. So you're just adding up the means, and we're going to, how many of them did we have? There was, how many of you guys again?
Did you write yours?
2, yeah, mine right here. 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. So should be divided by 28 as long as everybody put theirs up there like they were supposed to.
Should be what?
Should be 28 of them. Is this a 2.6 down there?
Yeah.
Is that 3.8?
I don't know what yours is. I don't understand how you say that. Divided by 28.
So this is our sample mean. Anybody get it? I got like 4.1.
That's what I got.
So did our sample mean come out the same as the population's mean?
No.
It was a little off, And again, the reason it's a little off, we got 28 here. We want to actually fit the theorem that we're going to learn today. We want at least 30 samples. All right, otherwise it's going to throw it off. And for whatever reason, probably because you don't like writing 8s and 9s, I was watching as you were writing this stuff up here, and a lot of you are picking the ones that have like a whole bunch of zeros in them. And so probably just picking easier numbers to write down for whatever reason. Maybe they were closer to the top of the page, who knows? All right, but you know, I watched a couple of them like this one right here. See that one, then you see some of these others that are a bunch of low numbers. For whatever reason, you picked a bunch of low numbers, so that probably put us down there. But the whole purpose of this is if we grab some population that's not normally distributed, so it doesn't actually fit that normal curve. If we do this, we can make it fit the normal curve by finding the means of all those little samplers, or all those little samples. So we can make it fit a normal curve. So like the U.S., if we're dealing with Republicans, Democrats, Independents, all that stuff, do you think it fits a normal curve that everybody's going to fall in this certain range? No. But we can make all that stuff fit a normal curve by taking a whole bunch of smaller samples and then combining them. All right, so figuring out the population mean, and then finding a whole bunch of little smaller samplers, 5, 10, 15, whatever it is, however many we're picking at a time, and then make it look like this. So our normal curve normally looks something like this. These sample means, the curve for the sample means is going to look probably more straight up and down. All right? So it's going to be, because what we're saying here when we're doing this is we're saying, all right, we ended up, when we did ours, we ended up here a little short of 4.5, somewhere over in here. But the more and more we do this, the closer and closer we're going to get to that mean of the population every time. All right? So this is what this is called is the distribution of the sample means, of all these sample means. So we're finding the mean, I have my pen here. We're finding the mean of all these different samples. Does that make any sense whatsoever? And what that does, it allows us to say that everything is normal. It's always going to be normal if we do it this way. Even if the original sample, let's say, let's erase all this. The original sample, let's say we graph the original sample, and the graph of the original sample looked like that. That's not normal. Even if the graph looked like that, when we take all these different little samples and we find the mean of each one, whatever the mean of this one is going to be the same as the mean of that one, but this one's going to look a little more normal, where everything is trying to get closer and closer to that mean. So sampling distributions of the sample means. Skip that. Let me get back. All right, sampling distribution. The probability distribution of a sample statistic formed when sample size n. Remember, n is just your sample size. So how many things are in each one? What was our sample size? What was our n? For the stuff we just got done doing. Be careful. Our n. How many numbers did you pick at a time? 5. So your n was 5. All right, your n was 5. Sampling distribution of the sample means. You got to remember this phrase. Sampling distribution of sample means. That's what all of this whole section is about. Oops. So you're taking a sampling distribution of all the sample means. All those means that you found, those were the means of the samples. Sounds confusing because sampling distribution of sample means, I don't know, it just sounds like something real mathematical or something. It's not as hard as what your mind makes it sound. So we're just finding the distribution of all those numbers that you just wrote up here in that second column. Something I should have done before we got off of that. How could I find the standard deviation and the mean of all our numbers on the calculator? I could have took all of the second column numbers, all the means, and put them into a list. And then found it using the 1 bar. So remember that's back from like chapter 3 or chapter 4. So remember that, how to do that, put it in a list on the calculator, and then do the stat, calculate 1 bars. Properties of the sampling distribution of the sample means. Move that down out of the way. The properties. This right here, that new symbol is mu subscript with the little X bar. That's the sample means. That's the mean of the sample. Mean of samples. Mean of sample means is actually what it is. So remember this is going to be different now. It's mu subscript X bar. But those two should be equal. This is the population mean. Population mean. What did we say the population mean was for our set of numbers that we had?
4.5.
4.5. Our sample means was what? 4.1. The mean of the sample means was 4.1. So ours came out to be 4.1 here. The population came out to be 4.5. Those two always have to be equal. You're not even going to have to worry about this. About half the homework tonight, it's going to say find the mu sub X bar. And all you're going to have to do is rewrite the answer. Because they're going to tell you, hey, the population was 4.5. Well, then what's mu X bar got to be? 4.5. They have to be the same. Yeah. They have to be the same. Stan, can you read that, or do I need to erase my stuff? Can you read it? I'll give you a second to write that down. This formula right here is important because you're going to have to use it a bunch. The means are going to be the same, but the standard deviation is not going to be the same. And it's not even called standard deviation when we're dealing with this. It's called the standard error of the mean. Standard error of the mean. So that sigma sub X bar is called standard error of the mean. Or just standard error would be fine. Standard deviation of the sample means, again, is sigma sub x bar. So both these go with the sample means. Mu sub x bar, sigma sub x bar. It's not equal to the population standard deviation. The way you're going to find it is you take the standard deviation of the population divided by the square root of your n, the square root of your sample size. So what was our sample size again? 5. So here we would put in a 5. And then we would just take whatever the standard deviation was of the population divided by the square root of 5. And that gives us the standard deviation of our sample. Actually, not standard deviation, it's called standard error. So if we have these numbers, 1, 3, 5, and 7, they're all written on sheets of paper and put in a box. 2 slips of paper are randomly selected with replacement. Find the mean, variance, and standard deviation of the population. Somebody do me a favor real quick, and just on your calculator, remember to find the mean, variance, and standard deviation. All we do is put this in a list. So put those 4 numbers in the list for me on your calculator, 1, 3, 5, and 7. And then you're going to hit stacked, 1 vars. Then you got to put in list 1, and then hit enter. We want to know the mean, which is x bar. Referring back to this, hopefully you remember some of this. What's x bar on there? 4. Then we also want, I don't know, is that right? Is 4 right? We also want the standard deviation. How are we going to find that? It's on there too, right? I think on there it's sigma x or something, isn't it? 2.23. Now, how do we find the variance? If they ask us to find the variance,
Square root.
be careful.
Square it.
You got to square it. So go backwards. What's 2.23 squared?
4.97208.
So about 4.97. So this is for the population. That's for the population, and this actually should be mu. I know the calculator tells you x bar, but it doesn't know that it's a population. So that should actually be mu. Then we have all that. That's for the population, for this set of numbers. What they're telling us to do is we're going to take 2 slips of paper. So if I went around the room with these 4 numbers in a bag, I'd say, okay, take one, put it back, take another one, put it back, you write down your 2 numbers. And we do the same thing we sort of did with our 5 digits there a few minutes ago. We should be able to do all this, and if we did it enough times, what should our mean come out to be? It ought to be real close to 4, right? So you could add up your 2 numbers, divide by 2, it should get close to 4 every time. But this is for the population. Got that? I actually did out longhand here using the formulas that we had back in chapter 4. That was our variance came out to be 5. Are we pretty close to 5 on our variance? Yeah, pretty close. Take square root of that, 2.236, pretty close. Again, I used all the formulas up here when I did it. We actually just plugged it into the calculator and let the calculator do it. It's going to be just a little different, but not a whole lot. If we graph those using the histogram, or I'm sorry, if we graph the probability using the histogram, remember our set Our set was 1, 3, 5, and 7. What's the percent chance that you drew out a 1 when I walked around with the bag? 25. How about a 3? 5. So when we graph this, what's the graph going to look like? It's going to all be just like that. The probability graph, the probability histogram, and even though, what's wrong with this histogram? They don't touch. I'm not sure why. I must have been lazy and picked somebody else's graph. They don't touch each other. They should touch each other. So it's just going to be all the same height for the probability histogram. So is this normally distributed?
Yeah.
Is that normal?
No.
No, it doesn't fit the normal curve. List all the possible samples. Don't let me forget, there's one problem on the homework where you have to do this. Also, there's a problem on the homework number 11. I believe it's number 11. Remind me at the end, we're going to get rid of it. Because it asks you to do this, and your list is like 70 or 80 things long. It's too much. So, I think number 12 does the same thing. Once you list them out, and the list is like 30-some long, so it's not real bad. List all the possible sample sizes with n equal 2. Well, if our numbers are 1, 3, 5, and 7, what two numbers could you have picked? Give me an example. 1 and 5 I thought I heard, then I heard 3 and 5. Is that all of them?
2 and 6.
Oh, no,
7. 1 and 7.
So there's all kinds of them, right? We could have picked any of those. And that's what it's saying. Make that list. This is what the list would look like. Do we just want to go at random when we have to make that list? What's going to happen if you go at random like we were doing right there?
You'll forget.
You're going to forget a bunch of them. So we do it this way, the way I made my list: 1, 1, 1, 3, 1, 5, 1, 7. 3, 1, 3, 3, 3, 5, 3, 7. So on, so on, so on. Just picking them. Once we have that, just like we just did, we'd add them together. This time we're going to add them together and divide by 2. 1 plus 1 is 2. 2 divided by 2, what's the sample mean there? 1. So we just find each mean of all those. Did all that, found the mean of all of them. These are your sample means. That's what we're looking at. If we wanted to stick those sample means into the calculator, into a list, we could find the sample standard deviation and or actually the standard error then, and we could find the mean of the population. Construct a probability distribution for the sample mean. So if we're looking at just the sample means, is it going to look like that other probability distribution did where all the things were the same height? No. Now it's going to be, if we do this, probability of just getting a 1, just getting a total of 1. If we go back, how many sample means was there that was just 1? 1 of them. How many sample means that are 2? 2 of them. About 5. How many sample means are there that are 5? 3. So the probabilities are going to be different for each of those. So that's our chart. That's our probability distribution like we made last chapter. 1 has about a 6% chance. Picking 1, then a 1 again. Getting 2 as your mean. About a 13% chance, so on, so on, so on. We graph it. Oh no, I'm sorry, we find the variance and stuff first. Find the mean, variance, and standard deviation of all our stuff. What do we know about the mean of the samples? Should be exactly the same as the mean of the population, which it was. The standard error came out to be 2.5. or I'm sorry, that's the variance. The standard error came out to be 1.58, which is going to be a little smaller. And what that's going to do, your original graph might look something like this. Your new graph, if the standard deviation is smaller, your new graph is going to look more like that, because if the standard deviation is smaller, you got less spread. You're saying, all right, every time we do this, we're going to keep getting more and more closer and closer into that mean right there every time. That's what we're looking at, is getting closer to that mean. Not so close to the mean here all the time. Well, here's all the, these are the ones for the, for our samples there. Mean came out to be the same. Standard error was 1.581, which is almost exactly the same. If we do it on the calculator, it won't come out to be quite exactly the same. But this one came out to be exactly the same because it was such a small example. We graphed the probability histogram. Now look at our histogram. What's true about our histogram now? Now it's normal. It fits that normal curve. Fits that bell curve. So we can change any set of data, even if it's not normally distributed, we can change it into this stuff to make it so it fits that normal curve. So even if we have something that looks crazy like that, we can make it fit that normal curve by using these sample means. This is the central limit theorem. Two things have to occur with the central limit theorem. Number one, your n's got to be greater than or equal to 30. So your sample size has to be greater than or equal to 30. Now I say it has to be, it doesn't necessarily have to be. We're going to talk about that here in a minute. There's two different ways it could fit this central limit theorem. If all your samples are more than or greater than or equal to 30, then it's going to fit this. So if you're taking samples and it's more than 30, it's going to end up looking like that normal bell curve, that normal curve that we've been dealing with. Says the greater the sample size, the better the approximation. So 30 will work. 3,000 as a sample size would be better. Notice these are all X bars. So what we're saying down here when we're on this is all those means that you found, that's what we're graphing now. We're not graphing the population. This is the population. Now we're graphing the sample means, the samples that you picked, like out of the back of the book. So again, there's two ways that you could, this central limit theorem. The first way, if all your samples are larger than, or 30 or larger, then it's gonna work. All right? The second way, if the original population is normal, then any sample you take will be normal. So if they say the original population is normal, you don't have to have your N to be 30 or more. It could be N is, like ours, our N was 28. That would have worked if the original set was normal anyway, which it was, so it should have been pretty close. So this is the second way that it could fit the central limit theorem. If the original population is normal, then the samples have to be normally distributed. So two things. Either you're taking samples larger than 30, or the original population is normally distributed. And they're going to tell you that in most of the problems. They're going to say something like, we take a sample of 35 males, and the population is normally distributed. Well, if they're saying it's normally distributed, then we can do all the stuff that we're getting ready to do. And one of those things is that we know that the mu of the population, the mean of the population, is going to equal the mean of the samples. They're always going to be exactly the same. And we know that the standard deviation of the population is going to be a little different. It's not going to be equal to. Standard deviation of the population is sigma, and the standard deviation of the sample means is going to be sigma divided by the square root of n. All this is still going to, still be the same idea. They're going to ask you for the area. What's the probability that we pick a sample mean that falls below some certain number? Well, for that right there, how much area is on that side of the graph right there? 50%. So the probability of picking something on that side would be 0.5, just like all the other stuff that we've been doing. In either case, the sampling distribution of sample means has a mean equal to the population. So the two means are always going to be equal. That's one of the key points. And this gives us the variance, but since we hardly ever deal with variance because we use our calculators a lot, the main thing is to remember that that's the variance. We don't even care about the variance. Standard error is going to equal sigma divided by the square root of n, which you wrote down on the other slide. So the means are always going to be the same. The standard deviation is going to be a little different than the standard error. The standard error should make it should be smaller because it's going to make it, instead of looking like this, spread out, it's going to look more like that. But it's still going to be a normal curve. So these two formulas, we wrote them down on the other. That's not really a formula, but those are the two things to make sure you have. So we start off with this. It's not normal. Some crazy population that we have here. We change it, it's going to look like this. Alright, what I'm going to do, I'm going to give you this assignment so that you can start on it. next time we'll go back over it. So Miss Clark comes in next time, she goes, oh man, I didn't understand about half of that. It's probably the way it should be. All right, go through, try it. Then we'll go over the rest of this PowerPoint next time, and I'll probably give you that same assignment again. That doesn't mean come in here, because if you come in here and you do nothing, you don't pay any attention when we go over the second part of it, you're not going to understand it anyway. So try it, because some of it you'll be able to understand with what we went over today.